I am recording this right now. I will post the recording later. We won't have the same issues we had last time. I now have the professional Zoom, paying for it myself. So that way we can keep on talking for longer than standard 45 minutes, okay? And I will load it once it gets stored, once it gets condensed into a MP4 file later, okay? All right, so I'm gonna share my screen and we'll be able to look at our exam. Let's do just this. All right. So can everyone see my screen of the exam? Okay. Okay. So we're going to go through just the exam piece by piece. All right. Please ask questions as we get through parts of the exam, so that way you guys can clarify any confusion. Okay. I expect there to be many questions because there seemed to be a lot of confusion. All right. So let's start from the top. We've got all of our molecules that needed to be given names. Okay, some of them, well, let's just say this, when it came to grading this section, I gave a lot of partial credit just because, you know, if you recognized one component of it, whether it was the parent name or even a particular constituent, or substituent, excuse me, I wanted to give you guys credit. So each of these was worth 2 points with the exception of our first one, which had, let's just say, oh, 5 to 9. With the exception of our first one, which had 3 points, because we also had to give E and Z, or R and S, for the chiral center and for the pi bond. I got a lot of students giving me R and S for this molecule here. Can you guys tell me why this molecule should not be given R and S stereochemistry?
It's not an alkene.
So alkenes are E and Z. So yeah, there shouldn't be any E or Z. Yeah, stereochemistry.
There's no wedges or dashes. There's no stereo.
Yeah, there's no chiral centers being indicated. While there are technically chiral centers, and so I suppose people correctly identify this and this are chiral centers, there is no way for me to know if the alcohol group is coming out towards me or away from me. And so this is not a specific stereoisomer. This is just a compound with many potential stereoisomers if I chose to write it, okay? The only one that I specified a chiral center for was this first one, okay? So hopefully we're all on the same page there, okay? Okay, so if we're writing out this first molecule's name, we should start, and this is just my strategy. I always like to start by writing out the parent name and then, you know, make some adjustments for there being pi bonds present or make some adjustments for there being substituents after that, okay? So what would be the parent of this compound? Got hex, okay. So hex is the 6th carbon system that this is a part of. Okay, so far so good. What is the rest of the parent? So I don't mean just how many carbons are there. I mean, what should I be paying attention to? What's the highest priority functional group? We usually have hex. We have number of pi bonds. So pi bonds, and then we have our functional group. And this is how we name a parent, meaning number of carbons, number of pi bonds, functional group. So who wants to help me name this parent? We have 2 pi bonds, right? They're positioned at what carbons? We know that if this is hex, this is 1. Let's just go like this. This is 1. And then therefore this is going to be 3 and 5. Okay, So yeah, exactly, Camille. This is going to be hex 3,5, okay, because we list those numbers at which the pi bonds begin, okay? And because I have 2 pi bonds, I'm going to call this diene, okay? And then the functional group of interest is not the alkene, okay? The functional group of interest is the alcohol. Alkene and alkynes have some of the lowest prioritization on our functional group ladder. Alcohols are some of the highest, or at least middle. They're not necessarily the highest, but they're up there, okay? They're definitely above alkenes and alkynes. So we're going to say, okay, well, that alcohol shows up on number 2, and it is 1 alcohol, so we say all, okay? This is the name of the parent, okay? And it's technically the name of the compound, the chiral center and pi bonds notwithstanding. So I gave you 2 out of 3 points if you just got the parent name correct. I took off partial credit if you got the numbering wrong, if you didn't put di with diene, if you didn't put the alcohol as part of the parent, okay, if you identified the number of carbons wrong, okay, but I gave partial credit for this. All right, the chiral center here is R, okay, the prioritization goes 1 for the OH, 2 for this branch here, 3 for this branch here. The hydrogen is branch 4, going away from us. 1, 2, 3, that is clockwise. So that means R is what we're looking at, and we would technically say, this is our only chiral center, so we don't have to give it a number, but if you did, you could put 2R. Again, you don't need the number. And then again, the only pi bond we have that is cis or trans is the 3rd one, and it is trans because I have both my groups away from each other, pointing in opposite directions. And so this is going to be E for trans, okay? ET, phone home, cis, and zis. All right, so this is the correct name of this compound, RE hex 3,5 diene 2-all. Okay. All right, there's definitely more than one way to name our second compound. Okay. I told you guys you would need to be able to name basic epoxides. This is one of them. All right. Does anyone know one method of how to name these? We have the oxirane method, or we have the epoxy method. Okay, so our first method could be the oxirane method. Okay, remember that, just see. This is what oxirane is. Okay, so let me move this up. This is oxirane. Okay, the oxygen is always going to be atom 1. And the other 2 carbons are going to fight for priority for 2 and 3, okay? So Grant is suggesting 2-methyl-3-propyl oxirane, and that's absolutely perfect, okay? The reason why oxirane is our parent is because, again, it's just the name of the epoxide. And then when we have our substituents, they are going to be prioritized alphabetically. Methyl comes before propyl. So we say 2-methyl-3-propyl oxirane. Okay. I did not take off any points for like extra hyphens or even just like mild misspellings. Okay. So just keep that in mind. That's one method for naming it. The other method is if we did it with the epoxy method. Okay. In which we look at the longest carbon chain and treat an epoxide like a substituent that's bonded to 2 carbons. Okay, in which case this would be the beginning, this would be the end of that carbon chain. The epoxide is bonded to position 2 and 3. So this would be 2,3 epoxy hexane. Okay, I did take off partial points if you misidentified the epoxy group as an S-oxy group. Okay, again, that's an ether substituent, not an epoxide substituent. Okay. When we're looking at this compound here, this is not an epoxide. This is not a ester. This is an ether. Okay, it's a cyclic ether, but it's a specific cyclic ether that we use often as a solvent and what you've used all the time in Orgo-1 reagents. This is tetrahydrofuran. If you just put furan, if you put hydrofuran, or if you just wrote THF, I gave you full points. Okay, if you made up some crazy name, I did not give you those points. Okay, so tetrahydrofuran, okay, or THF. All right, does anyone recognize what this molecule is? This fourth one over here? Sulfoxide, exactly. And you know what? If all you put down was sulfoxide, I gave you full points. Is that the name of this compound? No. This is a compound, again, that you use all the time in Orgo 1, and especially what we talked about this semester. It's a part of Swern oxidation. It's the only component of Swern oxidation I asked you about in this exam. Okay. Does anyone know the specific name of this sulfoxide? If you had to take a guess, they're right there on the molecule. This is sulfoxide. But the two things coming off the sulfur are dimethyl groups. So it's dimethyl sulfoxide, AKA DMSO. Okay. All right. This molecule over here was by far my greatest disappointment. Okay. This is a molecule that obviously I wouldn't expect you to name based on, rules of benzene, or it's certainly not an alcohol. Okay, this is definitely not an alcohol. I wouldn't expect you to name it based off of alcohol rules. What is this molecule? A couple students have gotten it or got it, but I would say out of like the 35 students who took the exam, 32 of you did not get it. Does anyone recognize what this is now? This is not a carboxylic acid. It looks like one. It has an extra oxygen. So it's a per acid. I told you that it had a chloro at the meta position, metachloro per benzoic acid, MCPBA, exactly, okay? Which I chose not to ask you guys about the MCPBA mechanism, but I wanted you to at least recognize the structure. MCPBA, also known as metachloro per benzoic acid. Okay, if you identified the chloro was at the meta position, if you identified that this was a per acid, I gave you partial credit. Okay, if you recognize it as MCPBA and just put MCPBA, I gave you full points. Okay, not many people did that. What about this second to last one? What type of functional group is this? You can come up with it two different ways. One method is good for naming, the other one is not. So diol, exactly. Okay, some of you put glycol, in which case I think I gave you partial points. But again, this is not a glycol that forms from a small, simple alkene. So we wouldn't name it as a glycol, okay? But we would certainly name it as a diol, okay? And of course, some of you guys struggled again trying to figure out how to number this. Some students just try to name it as an alcohol and list this as like a hydroxy functional substituent, okay? If we have two of the same functional group, all we have to do is put a di in front of the ol, or a di in front of whatever it is we're dealing with. So in this case, my parent is going to be 1, 2, 3, 4, 5, 6. Okay, it's a hex. There's no pi bonds. I'm just going to put ane. Okay, and then we could put 2, 3 diol. Okay, pretty straightforward name. All right, if you chose to say 2, 3 hexadiol, that's totally fine too. Or if you put 2, 3 hexane diol, that's fine as well. Okay, there's no other things to number here, so you could put the numbers in front, or like in front of the name, or in front of the actual functional group. All right. All right. Now this last one was the only one I asked you guys about that required you to name phenols. So again, some students were struggling to identify a phenol, and we're calling this hydroxybenzene, or even trying to name it as an ether with like an ethyl phenol ether. But no, this is just us naming a phenol, okay? Where we have, I think if you tried to name it as an ether and you put ethyl phenol ether, I gave you partial points. Again, not appropriate because I wouldn't know where on this phenol I was branched at, okay? Which is why we say the parent is going to be phenol, and ether, the ether is going to be a substituent, okay? What would be the appropriate number for my ether substituent here if phenol is my parent? of 3, exactly, Camille. Okay, we start at position 1 where the phenol is our highest priority substituent. And then we've got 2, 3, okay? And then what is this alkoxy group called? Ethoxy, exactly, okay? So 3-ethoxy phenol is just the name of this compound, okay? So guys, none of these names were that terribly difficult. The first one was difficult. 3 of these literally just needed you to recognize. I would have given you full points if you just put the acronyms for them, okay? But you should be able to recognize and discuss these molecules when we learn about them, okay? So this is important. Okay. Any questions on the naming before we move on? Feel free to type it out or just turn on your microphones. Okay, either is fine. Oh, so admit some people. There we go. Okay, sorry guys, I just saw you in the waiting room. So we just finished going over the naming portion. Okay, the answers are here. Okay, so does anyone have any questions before we move on? Anthony is saying, okay, the last one you saw is an ether. And so guys, just keep in mind when we name ethers, ethers are only going to be the name of the molecule if it's the only functional group on the compound. Ethers are almost always like the bottom of the barrel as far as functional groups are concerned. They're so inert, we just don't pay much attention to them. And so it's because of their inertness that they fall to the bottom of the priority as far as naming is concerned, okay? So if this was the only functional group on here, great, we could name this as this R branch and this R branch. Say the alcohol is gone, we could say, okay, this is a an ethyl phenyl ether. That would be the name of it. But because I have a functional group that has a higher priority, then my ether becomes a simple substituent, okay? And then I say, okay, my phenol is my parent, and then ethoxy becomes my substituent, okay? Hopefully that makes sense. Okay. All right, so for question 2, something that seemed to perplex just a couple of students, or at least some students didn't read, is that I was asking for alcohol. Okay, I wasn't asking for carbonyl groups. I wasn't asking for ethers. And on top of that, I wasn't asking for phenols, which I got from almost every student. Okay. And something we needed to pay attention to as well was the number of hydrogens. Okay. So for those of us who aren't aware when we're drawing our isomers, okay, all isomers, because they have the same molecular formula, are going to have the same degrees of unsaturation for every molecule. Meaning if one of my isomers has a pi bond or a ring, aka 1 degree of unsaturation, then all of my isomers also have to have a pi bond or a ring, 1 degree of unsaturation, okay? And so if we calculated here, the DOU, degrees of unsaturation for this molecular formula, 2 times the number of carbons, okay, plus 2, minus the hydrogens, okay, we'd also minus halogens and add nitrogens if we had them, but we don't. This is all going to be over 2, okay, and so this is just going to be 2 times 4 is 8, plus 2 is 10, minus 8, okay, we can already see here this is going to end up being 2 over 2 equals 1. Okay, so 1 degree of unsaturation, meaning 1 pi bond or 1 ring for all of my answers. Okay. When I graded this, okay, 10 points was for someone who got it absolutely right. Okay, I gave 7 points for the structures that were there. I gave an additional point if you didn't give me any duplicate structures. I gave you an additional point if you didn't give me any enols. And I gave you an additional point if they all had 1 degree of unsaturation, okay? So there's gonna be a variation in grades for this one. And the good news is, or not the good news, but something interesting here is I said that there were 7, but there actually were 9. So there, you could have come up with even more than what I said. So let's start by just starting how to figure this out. So we know that there's 1 degree of unsaturation so far. Okay, so I'm looking for any alcohol, again, not an ether, not a ketone, not an aldehyde, not a enol, with 1 pi bond or 1 ring. Okay, so we can immediately just start doing rings to keep it easy. Okay, so let's just say I've got all 4 of my carbons in 1 ring. Okay, and then I'm going to make my alcohol group just come right off. Okay, and then we'll have my OH. Okay, so this is one of the answers already. Okay, this is cyclobutanol. Then I could have said, okay, well, we can make a smaller ring as well. Let's do a 3-membered ring. Okay, and then off of that 3-membered ring, I could have had my methyl group. Okay, I could have also had my alcohol group. Okay, then off of a 3-membered ring again, okay, I could have had my methyl group and my alcohol be just simply 1 substituent. Okay, I could have had my methyl group come off of a different carbon than my alcohol. Okay, these are my 4 potential isomers that are just using rings. Okay, I can't make a 2-membered ring, so we're going to stop at a 3-membered ring. Okay, when I'm doing my linear isomers is when we have to be a little bit more careful. Okay, first of all, I can use all 4 carbons in a row. Okay, and the last bond can be my alcohol. Oops. Okay, but again, I need 1 degree of unsaturation. So I'm just going to put my pi bond at the end. Okay. Oops, not like that. There we go. Okay. So that's one method. Another method is I could have had my alcohol be 4 carbons in a row, but I could have had my pi bond be just say, oops, let's redo it. Could have had my pi bond be on between carbons, let's see, 2 and 3. Okay. And immediately I could have had this be cis or trans. Okay. Just doing these 7 alone would have gotten me full points. Okay. 1, 2, 3, 4, 5, 6, 7. Okay. But what's wrong with this? Right. What's wrong with this being an isomer? You can't have an allylic bond. Exactly, Grant. I cannot. Okay. And this is technically not allylic. This is vinylic. Okay. This is allylic. All right. Meaning I'm 1 sp3 carbon away. But yes, I can't have a vinylic bond. Okay. Why? Because that means that this is no longer an alcohol. This is an enol, which is a different functional group. Okay. So this one would not have worked. Okay. What I can do instead is have limited this now instead of doing a long carbon chain, I could have done a 3-carbon chain. Okay, and then I could have had a substituent on carbon 1, okay? Or I could have had a substituent on carbon 2. Okay, and then my pi bonds could have been either, say, pi bond could have been here. Okay, or my pi bond could have been here for this one. Okay, these are the only positions that my pi bonds can be at for these structures, because if my pi bond was here or here, again, that would be vinylic. And if my pi bond was here, that would also be vinylic. And if my pi bond was here, that would be a duplicate of this structure. Okay. Lastly, I believe there is one more. Let's see, we have 1, 2, 3, 4, 5, 6, 7, 8, 9. Nope, these are all of them. Okay. So these are excuse me, all the structures we could have done with at least 1 degree of unsaturation. Okay, I can't bring my alcohol any smaller than 3 carbons in length with 1 substituent, because then I would need to do, let's just say 1, 2, 3. This is the only other substituent I could do with 4 carbons and an alcohol, but obviously this means that I wouldn't be able to have a degree of unsaturation. Okay, because all of my carbons are fully bonded at this position, or my carbon at this position is fully bonded. I can't put a pi bond anywhere. Okay, so okay, everybody understand how we were supposed to approach this problem? Okay, hopefully. All right. When it comes to this third question, okay, I got a lot of people ranking, but I got a lot of people, again, not reading the directions. So not everyone gave me names for these structures, which were really easy to name if you knew how to name ethers. Okay, so naming was 4 points, ranking by boiling point 6 points. Okay. All right, all you had to keep in mind is that there's multiple ways to have name names. The simplest way to name them is by just identifying the 2 R groups, alphabetizing them, and then saying ether at the end. Okay, again, this is how we can name ethers when they're the only functional group in the compound and they're components of simple R groups. Okay, so this would be, for example, what would be the name of this first one? We have an isopropyl group and we have a methyl group. Okay, if we were going to name it according to the method I was just describing, where ether is the parent, okay, isopropyl versus methyl, isopropyl comes first. Okay, iso is a part of the alphabetic system for those common names. Iso and neo are considered a part of the name, whereas tert-butyl and sec-butyl are not. But is the beginning of that. We don't include the numerical prefixes. So this would be isopropyl methyl ether. The other method is what Grant mentioned, 2-methoxypropane would also be fine, okay, where we name the substituent methoxy coming off of the parent, which is propane. Okay, either of these were accepted. Okay. Methylpropyl ether, Camille, the only problem with that is we don't have the isopropyl. Okay, again, we have to be mindful of the substituent saying we're coming off of the iso position. Okay, if we're looking at the third ether, this is propyl. So this would be methylpropyl ether. Okay. And then of course, the second way we could name it, if we said propane was the parent, this would then be 1-methoxypropane. Okay, I accepted either again, okay? And then this fourth one, again, just another simple method of saying, okay, I have an ethyl branch, I have a methyl branch. This then is going to become ethyl methyl ether. Okay, another way we could have named it would have been methoxyethane. Okay, you could have said 1-methoxyethane, meaning that we were coming off of carbon 1 of the ethane branch, but again, it didn't matter where we identified us being branched off because there's only 2 carbons. If we branched off of this one or this one, aka 1 or 2, we would still get the same compound. Okay, so methoxyethane is also an appropriate way. Okay. Something I just want to mention quickly. First of all, let's just finish naming. Of course, this is butanol. Okay. If you wanted to name this 1-butanol or N-butanol, okay, either of these were fine. This is not pentanol. This is not propanol. Okay. Excuse me. I have to get used to counting the number of carbons appropriately, okay? Sorry about that. Okay. And then the last thing I want to mention about naming before we talk about the boiling points is for this first compound, some people would just put isopropyl ether. All right. If you put only one R group for an ether, it's implied that it's the R group on both sides of the ether. So for example, isopropyl ether is just an inappropriate way to say actually diisopropyl ether, which would be this compound. Okay, this is diisopropyl ether, otherwise sometimes incorrectly named isopropyl ether. Okay, again, we want to indicate the methyl is there because that has to be the other R group. Okay, not every ether has a methoxy group on it. Okay. Okay. Let's just so we're clear. All right. When it comes now to naming or not naming, but to ranking by boiling point, okay. A couple students just, really nailed it. And some of you guys just didn't quite seem to either pay attention to the maybe one being the highest. I wasn't quite sure what the issue was, but I was surprised at how many people didn't understand that butanol would have the highest boiling point. Okay. The first thing we pay attention to when we're talking about boiling points is our molecular weight. Okay. Heaviest equals highest. Okay, this just has to do with the amount of London dispersion forces that can be present. Okay, so if I have more electrons in my compound, I can create more instantaneous dipoles and my molecules can be more attracted to each other. Okay, this is why we generally only ever compare molecules of somewhat comparable or similar molecular weights when it comes to just looking at the intermolecular forces, because we have to assume, again, that the molecular weights are roughly the same before we look at only the molecular forces, right? So molecular weight comes first, then we pay attention to IMF, okay? So strongest equals highest, okay? So hydrogen bonding is going to be higher than just simple dipoles, okay, which is going to be higher than just simple London dispersion, again, assuming the molecular weights are roughly the same. So if we look at just the molecular weight, we could have said, okay, well, I've got 4 carbons and an oxygen, 4 carbons and an oxygen, 4 carbons and an oxygen, and then I've got 3 carbons and an oxygen, okay? This one should immediately be last place, okay? So this one's gonna be 4 because it weighs the least, it's gonna have the lowest boiling point, and it does. This boiling point is, and let me, instead of doing that, this one is got a boiling point of like 7 degrees Celsius. Okay. When it comes to the highest, okay, all of these being equal comparable molecular weights, we can say the alcohol is going to be the highest because its molecular weight, or excuse me, its intermolecular force is going to be hydrogen bonding. Okay, alcohols compared to ethers can hydrogen bond with themselves whereas ethers cannot. They can hydrogen bond and be more soluble in water or, protic solvents, but they themselves cannot hydrogen bond with each other. Okay, this is going to be the highest, aka number 1, and its boiling point is going to be around like 120. Okay. When it comes to differentiating between these two, okay, one is a little bit more linear and one is a little bit more branched. Okay, at this point, the branching is going to contribute to the amount of effective stacking and London dispersion that a molecule can contain within a solution. So branching, okay, we can say branching equals, branches equal bad, I suppose, in terms of like effective London dispersion. So we can say branches equal say bad LDF, leading to low boiling point. Okay, so in this case, notice that it's the lowest component on our list when it comes to molecular weight, IMF, and then branching. Okay, and it's going to make the biggest, or excuse me, the littlest difference when it comes to the actual effect on molecular weight. So this methylpropyl ether, the third one, is going to be the second highest, again, because it doesn't have branching. It is going to have a boiling point of around 39 degrees, okay, around like 40-ish, okay? And then the isopropyl methyl ether is going to be the second lowest with a boiling point of around 31, okay? So notice the effects of these boiling points and the reason why they fall in this order. Again, our molecular weight plays a big role here, okay? All of these, the first 3, all have the same molecular weight because they have the same molecular formula. They're just isomers of each other. The biggest difference here is that butanol can hydrogen bond with itself. And look, that blows up that boiling point by like 90 degrees. These guys are hanging out around 30 or 40. So 80 to 90 degrees more than that is where the alcohols hang out. When it comes to something that's a lower molecular weight, right, this is somewhat comparable in structure to just the one right next to it. But we can see, again, look, we've dropped another 30 degrees just by taking away a carbon. We didn't change the branching. We didn't change the intermolecular formula or intermolecular forces. All we did was take away carbon with 2 hydrogens. And we now have 30 degrees less as far as the boiling point is concerned. All right. And then lastly, the branching, which has the least effect, but still is something we need to pay attention to. Okay. Methylpropyl ether is around 40. Isopropyl methyl ether, aka one more branch, is 10 degrees lower than that. Okay. So this interrupts the nice, neat stacking that this isopropyl methyl ether can do with itself. This one cannot effectively stack and not effectively have those instantaneous dipoles help build up these intermolecular forces. So we see 10 degrees less in terms of where the boiling point is, okay? All right, any questions on how to rank? You feel okay about that? Yes, okay. All right, question 4. This one was by far the saddest question. Okay, it was the simplest and almost no one got it. I gave you guys, so the way this question broke down is 1.5 points for each one. All you needed to do was give me a base that fully would deprotonate each of these structures. Again, something that you guys worked on in a recitation assignment just like a week ago. So you just need to give me an appropriate base, and you get the other half point if you just at least gave me 3 bases, even if they weren't, the right base. So you got a half point for just giving me bases. You didn't get that point if you gave me, for example, acids or some other random reagents, which I did end up getting. Okay. When I ask for a base, I do not mean a reducing agent. I do not mean, I certainly don't mean an acid. A lot of people gave me chromic acid. It literally says acid in the title, guys. So again, I'm giving you a hint. use it. Okay. So the only way you could have really effectively have done this question is by knowing the pKa's for these three common molecules. Okay. And then ideally understanding and knowing the bases that have conjugate pKa's for their acids. All right. The pKa of a terminal alkyne is, let's just get this here. Where's this text box showing up? Let's do it this way. Okay. Okay. The pKa for terminal alkyne is 25. Okay. What's the pKa of a phenol? 10. And what's the pKa of a tertiary alcohol? Think of like terbutanol. 18. Okay. So in order to fully deprotonate these, I need to have bases with a conjugate base that is higher than these pKa's. Okay. That's the only way to effectively fully deprotonate. Okay. Ideally, there's at least maybe, you know, a pKa of like 5 to 10 higher, but even if you just gave me a pKa of like 1 to 2 higher, I would have accepted it. Okay. So what is wrong with using NaOH for this first one? Why can I not use NaOH to deprotonate a terminal alkyne? Not strong enough. What is the conjugate acid of hydroxide? Just say this picks up a proton, right? It behaves as a base, it picks up a proton, it turns into water, right? Stuff we drink all the time. The pKa of which is 15.7. Okay. There was only one acid on here that would have worked with hydroxide, and it's the second one. Okay. I could use NaOH, that's fine, because the conjugate acid is 15.7, and that's higher than phenol's pKa. Okay. What about a couple others? A lot of people gave me water. Would water have worked for any of these? Just to be clear, if water had picked up a proton, it would form H3O plus. This has a pKa of -2. Okay, so this would not have worked for any of them. We're just gonna put this aside and say, no, 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 no way, Jose. Okay. All right. Meanwhile, Grant was suggesting sodium hydride. Okay, that would have worked great for either of these. Okay, so let's just say NaH, I pick up an H plus, it becomes H2. This is a pKa of 35. That's fantastic. So I could have used this for a terminal alkyne or for an alcohol. Okay, and then what's another great one? DBU. So DBU does not have, so DBU is a bulky base, but it's not a particularly strong base. Okay, I think the conjugate pKa of DBU is around like 6. So DBU would not have worked. Okay, but there is a better one that you'll see all the time in the textbook, especially for deprotonating terminal alkyne. So even if we move this over here, kind of like a la Williamson ether synthesis. Okay, there's another one. Okay, so cyanide would not have worked. Cyanide is the conjugate base of an acid. Okay, so cyanide is not a very good base. I think its pK is around like 9 for the acid, that is. Cyanic acid. Let me just check. Yeah, so hydrogen cyanide, it has a pKa of 9, so that would not have worked. Okay. What's the one that the textbook uses all of the time, especially to deprotonate terminal alkyne? About NH2. Conjugate base would be NH3. Okay, this is a pKa of around 38. Okay, this is like the base du jour of Orgo 1. Okay, so these are the appropriate bases we could have used. Okay, H2O, cyanide, DBU would not have worked. Okay, again, we need to be mindful of what the pKa's are so that way we can manipulate acid-base reactions appropriately. Okay, again, these are like 10 numbers you guys need to memorize. That's it. Okay, any questions on the first page before we move on? Okay, all right. Question 5. Question 5 was all about explaining the Williamson ether synthesis and why it's not used to make this particular molecule, and then how do we provide a different method? Okay. Again, some students briefly explained why this couldn't be used. They briefly described it one way only. And then some students just never gave me a different method, or if they did it in a very vague way, which I did not provide any points for if I couldn't understand what you were trying to recommend. Okay. Why can this molecule not undergo Williamson ether, or why can it not be formed from Williamson ether effectively? When we were in class, the way that we decided how to determine potential pathways to form a molecule from Williamson ether synthesis is by looking at both branches. Okay, we can have that particular branch, in which case we have let's just say a benzyl molecule. Bear with me as I try to figure this out. No. Okay. Good. Yeah, okay. We have a benzyl molecule. This could have been bonded to a bromine. Okay. And then the other component, of course, would have been the alcohol. So our oxygen here. Okay. So this could have been our two components. All right. So if this was one particular component, what's wrong with this? So Grant's saying that this is sterically hindered. So this is a secondary alkyl halide. This is not the issue. Steric hindrance is not the issue. What is the issue here? What type of hybridization can undergo SN1 and SN2 for this molecule? Because if this was my structure, I'd use this as my nucleophile, right? Just be clear. I can do this. No, I guess not. Okay, I'm trying to figure out how to do doodles on this. Okay, kind of a lone pair. Oh my God, it's not even worth it. Okay, so let's just say this is a negatively charged oxygen. This is my nucleophile. Okay. This would need to attack this carbon. Okay. we cannot attack this carbon. Why? Why can I not attack this carbon? Yeah, it's sp2 hybridized, exactly. Okay, SN2 is only able to work for sp3 alkyl halides only. Okay, SN2 and SN1. Okay, this bond is simply too strong between an sp2 carbon and a bromine for this to behave as a good leaving group or for it to be a good electrophile. Okay, I can't do that. So this would not work. Just say no dice. Okay. The other pathway, well, what happens if I throw here? Okay. And that would give me phenol or phenoxide as my conjugate. No, not that. Okay, so this would be my nucleophile. And the electrophile would be, if I had what we were talking about to begin with, okay, which would be if this one was my alkyl halide, right? This would be the problem in which what Grant was saying, or Camille, that this is too sterically hindered of an electrophile, and so it would prefer E2, Camille correctly said, okay? When our strong base nucleophiles or even something like phenoxide goes to attack, this is not going to be able to undergo a reaction in which we directly attack this molecule. Williams made this is best used for SN2 reactions. This is simply too sterically hindered. Okay. What would have been an appropriate method for this reaction to get this particular molecule? Two methods would have worked. What would have been a good one? Okay, some people got it. I'm just going to write it out. Okay. The method for doing this would have been to recognize that we still needed our alcohol from our phenol. Okay. Can we just, thank you. I tried going outside my window right now, so funny I can hear the loud cheering. It's a happy day. Okay. Okay, so then we have our alcohol. Okay, and then we would have done this reaction. With either an alkene or a alcohol in acidic conditions. Okay, so whatever acid catalyst you wanted to use, you didn't even need to list one. You could have just said acid. Okay, you didn't even need to show me the mechanism, which I'm grateful some of you did. Okay, the way that this works is the acid would catalyze this reaction by either adding a proton to an alcohol that would then leave by turning it into water, right? This would be protonated, it would turn into OH2 plus while it was bonded, and then it would leave as water, creating a carbocation. The other alternative was to have just a simple alkene, okay? And we could have had more than one. You could have had the pi bond off on one of these branches or the pi bond that was tri-substituted. Either would have been fine, okay? So this would have been fine. If the pi bond was on one of these two carbons, that would have been fine as well, okay? The point of either of these being with the acid was to generate a carbocation. Okay, and then this would be where our nucleophile attacked, and we'd be able to form the potential ether we wanted. Okay, so hopefully that clears that up. Okay, again, this would just be acid catalyzed addition to an alkene or to an alcohol to form the particular ether of interest. All right, this is one of the few ways that we can actually form a tertiary ether. All right, everyone understand that now? Okay. Now, what about question 6, in which we have the formation of this compound via Grignard? Okay. So something that seemed nice was that it seemed like a lot of students did understand this concept, and it seemed like a lot of students thought they understood it, but definitely did not understand it. Okay. Grignard reactions are going to come back and keep coming back the entire semester. So if you do not get them, please come talk to me and we'll figure it out. Okay. But this is something you need to understand. It's super important for synthesis questions. If you don't understand it, you will not pass this class. All right. So for Grignard reagents, we need to recognize there's 2 different methods, at least that you guys are aware of right now, that we use Grignard to attack either carbonyl groups or epoxides. Okay. There were multiple methods for forming this. Okay. And you could have chosen any number of them, but again, you needed to just write out 2 potential ways to form this molecule. Okay, so if I was just looking at this carbon here, okay, and I said, okay, what if it's derived from a carbonyl group? Okay, then what I could have said was, okay, well, the carbonyl group needed to be obviously this carbon and this oxygen. That's all carbonyl groups are. Oops, not colored in. Okay, but then my Grignard reagent could have either been the methyl group that attacked this carbonyl that was bonded to this R. Okay, or it could have been, this is my Grignard reagent that attacked the carbonyl group already bonded to this R. Okay, so all I have to do is say, okay, well, here's one option in which we have a 5-membered ring. There we go. With these bonds coming off of them. Okay, and then off of this could have been my magnesium bromide. Okay. And if you wrote the bromine and then turned it into a Grignard, that was fine. Okay. Nope. No. Okay. So this would have been MgBr, indicating that this, so let's just say this was our nucleophile. Okay. This was going to attack the carbonyl that I chose to write out. So let's just say this is going to be my carbonyl. Okay, where we'll have an oxygen here. Okay, and it will be bonded to a methyl group. Okay, so this is all I had to put for half of the points for this question. Okay, this was my nucleophile, and let's just say over here, this would have been the carbon electrophile. And again, I didn't even need you guys to identify this. I'm just showing you so that way we understand what's being attacked. Okay, nucleophile, electrophile. This is the new bond being formed. Okay, and then in order to form that bond, we have to accommodate by opening up that. Okay, again, I didn't need you to show arrows. I just needed you to show me the structures. The other method we could have used, again, was instead of using this as our R group and this is our carbonyl, we could have had the carbonyl be right here and methyl be our, or I guess not right there, but let's see. of it. Okay, so we had here, 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 and then here. Okay. Next. All right. So this would have been our carbonyl. Right. This would have been the carbon that we attacked. And my Grignard reagent simply could have been a methyl Grignard. So MEMGBr. Okay. And then this would have attacked here, and this would have opened. Okay. The other method we could have used would have been using an epoxide. Okay. And this could have been if I had, just say, this is my Grignard. Okay, and then what I would have attacked would have been my electrophilic epoxide, which we know at least is always 2 carbons. Okay, and I bind at the beta position of the alcohol. So if this is going to be the alpha position, then this is my beta position. Okay, which means this has to be the position I attack of the epoxide. Okay. No, there we go. Okay, so if this is the carbon I'm attacking, obviously you can see that's just a circle and the big squiggle. Okay, so that's the carbon I'm attacking. We also have to keep in mind that there are other R groups on this carbon. Okay, one of them is this branch here, and the other one is a branch right here. Okay, so this is just a, what do we call it? Symmetric epoxide. Okay, this would be 2,3-dimethyl oxirane. Okay, so these are 3 possible ways that we could have formed this. Okay, and there are other ways to have done it as well, but these are all the 3 major ways we could have done this through Grignard. Okay, all right. For this question here, okay, I haven't finished grading this. Actually, no, I did finish grading this page. I think probably like 3 people out of the entire class got this mechanism. It's a little bit disappointing. What does this reagent do? Anyone tell me what it does? Especially under heat conditions. What do alcohols do under conditions such as aqueous sulfuric acid? Anyone? Elimination. Exactly, Regina. Exactly. Okay. We're always going to be in this equilibrium between, let's just show a potential molecule that we could have had here. Okay. Pretend this is a hydrogen. Oh my God. How do I try? Okay. Yeah, that's what we're going to do. Okay, here we have our OH. Ignore my huge O and my tiny h. The point is that we've got an alcohol group and we've got acid. Okay, what is the actual acid in sulfuric acid? sulfuric acid in water, what is going to be my actual acid? Okay, if we have H2SO4 plus water, the actual acid-base reaction that's going to form is going to be HSO4 minus and H3O plus. Okay, these are going to be the two things that I'm dealing with, and the actual acid in H2SO4 is going to be hydronium. Okay, this is what we should have used to do our elimination reaction. Okay. I gotta be honest, I was so disappointed with this that even if you just put the alcohol somewhere else and showed like an isomerization of this, I gave you like full points, okay, or like nearly full points. So we have let's just say OH2, that makes this a positive here. Okay, I did take off points for formal charge. Again, not that it really mattered because so few people got this or attempted this that it's almost like I didn't even notice. Okay, so we will remove the proton from there. And the electrons would go to oxygen. Something worth considering is that we did an entire recitation worksheet on the mechanism problems and where arrows should be moving and where arrows should not be moving. For those of us who at least attempted the first step of this reaction, the number of arrows I saw going in this direction was troubling. Okay, this is the wrong direction. Okay, the same exact thing that we talked about in class on the recitation worksheet, this is the wrong direction. I cannot have an acid, which is giving me an H plus, be donating electrons. Okay, this is not how we show acid-base transfer. We show a base picking up a proton and then giving electrons to the acid. Okay, this is how acid-base reactions always work. They're always two arrows, base picking up a proton, acid receiving electrons by giving up that proton. Okay, always the same. Again, if you are not understanding this, come talk to me. You will not be receiving full points for mechanisms for the rest of the semester if you don't understand this one point. Okay, then once we get our protonated alcohol, so we have OH2, so to speak. Okay, you could have written it like this, or you could have written with two hydrogens coming out, but now this would have been positive. Our formal charge would have been plus. Okay, now as long as I'm forming at least a secondary or tertiary carbocation, or even a primary with a lot of resonance, then I can just have my water leave. Okay, so water leaves. I get my nice secondary carbocation. Okay, what's something in the mechanism I'm drawing right now that I don't need to consider, or not necessarily don't, but let's ask this actually different way. What's something I need to consider every time I have a carbocation formed? Rearrangement. Exactly, guys. Okay, so in this case, if I were to rearrange, I wouldn't be improving the stability. But for the sake of the question that we are actually working on, if this water left and then this was the carbocation that I ended up forming, would I need to consider rearrangement? I would, right? Because I'm secondary, but I can move next door and be not only tertiary, but be tertiary benzylic. Okay, so this is a no-brainer. And then something some students put was just, okay, they understood that rearrangement needed to happen. And then they're like, okay, great, rearrangement needs to happen. So let's do that. And then we'll just draw our structure. Like this. I'm just gonna put a circle in the center. Okay, and then we have this. Nope, not an arrow. Okay, and then some people just said carbocation rearrangement. and then just put the carbocation there. Okay. And while I applaud you for recognizing that a carbocation would rearrange, you have to give me a reason why. How does this rearrange? Okay. How? How does the positive move? It doesn't just move by itself. Positives are not anything. Positives are an absence of something. Okay. So I need to show the electrons moving from somewhere to fill where that previous positive was. Okay. In this case, we could do a hydride shift very easily. Okay. So we put a hydride here, or hydrogen here, and then we move the electrons to where the positive is. Draw my arrow. There we go. So this is how I show a hydride shift. Okay. Where we have the electrons holding a hydrogen to a neighboring carbon, shifting over. Okay. And then that hydrogen is now bonded with the electrons next door. Okay. You didn't need to show the hydrogen. You just needed to show the hydrogen shifting. Okay. Now we have our new positive. Okay. Because I'm in heat conditions, okay, I'm going to now form my final product via elimination. Okay. This is going to be by removing a hydrogen to form a pi bond. All right. Water, which is going to be behaving as my base here. I have water as my base, and I got hydronium as my acid. Okay. What proton do I want to pluck off of this? I've got two different types of beta protons that I can remove. The one that I just shifted, or I can remove this one over here. This is the other type of beta proton I have. Let's just say I've got the red one, or I've got the blue one. Yeah, exactly, Grant. Light sub product is going to be preferred because I have a small base. I'm going to prefer to remove the more sterically hindered proton to get the more substituted alkene. Okay, so this is going to be a 2-arrow system. We have H2O behaving as my base. I'm going to use its lone pairs, which I'm not going to draw right now because I'm on preview. Okay, which is going to pluck off this proton. And then these electrons carrying it are going to go to this neighboring carbon. Okay. This is how we do the last step of an elimination. And then, of course, my final product is going to be this elimination product. Okay, so this should have been my final product. If you put the final pi bond on this position, all I did was take off 1 point. Okay, so otherwise, you know, you did great. Okay, but this is the general gist for this mechanism. Okay, we will be protonating the alcohol, having it leave as a leaving group. We'll have this carbocation now. Depending upon our conditions, we'll either have the alcohol reattaching if we have, for example, a lot of water present for like a dilute solution at low temperatures, or we'll have water behave as a base and remove a hydrogen to form a pi bond in both concentrated situations, like less water is there, or if I have heat, which is already going to favor elimination. Okay. All right. Question 8 had to do with the reactivity of the Diels Alder. Again, we already talked about this in class. I'm not going to harp on it. Our Diels Alder reactivity needs to be in the cis conformation for diene. When we're locked in an S cis, that is the best. So this is therefore going to be the most reactive. Okay, when we are locked in an S trans, we are therefore going to be not able to do Diels Alder at all. So this is going to be our least reactive. Okay. Otherwise, we just have to be able to say, okay, well, when I rotate these bonds, you know, to maybe see how the would look in S-cis conformation, well, I need to say, okay, well, this bond is trans and this bond is trans. So when I put it in S-cis conformation, then I still need these bonds to be trans, which means that in this case, the R groups are facing out from each other. Excuse me, that's the wrong pi bond. Pi bond here, pi bond here. Okay, these still need to both be trans. So notice this R group and this R group are pointing away. This R group and this R group are pointing away. This is the structure here. Our two R groups are facing outward. This is a low energy conformation. Whereas here, when I rotate these guys inward, they're both cis. Okay, so when I make this the S-cis conformation, it's going to be relatively high energy. Oh, come on. Okay, this R group is going to be facing inward, as is this one. Okay, it's going to have some steric hindrance. We're not going to favor being in this S-cis conformation. We're going to prefer to be in the S-trans more often, meaning that we're not going to have a likelihood of doing Diels Alders. Okay, still not as bad as being locked out completely like we see in that second structure. So this is going to be 2, and this is going to be 3. Okay. All right, question 9. Okay, this one, I literally couldn't have set it up better. Guys, this is literally, you're just given a chromium reagent. You're given a primary alcohol that's bonded to it. And I ask you to show me the mechanisms. I think I probably said this about 5 times over the last like 2 weeks, over what mechanisms you would need to know. If anyone asked me, I asked you to get to know this part of the mechanism very closely, just this one step. Okay, what is this reagent? We have chromium, we have pyridine. This is PCC, okay? Pyridine chlorochromate, okay? When you learn about a reagent, learn about it, okay? PCC is pyridium chlorochromate, okay? So here you see your chlorine, here you see your pyridine, here you see your chromate, okay? This is not simply chromic acid, because then we wouldn't have these components here, okay? Nor would you have a negative chlorine, okay? So in this case, what we're going to be dealing with is our chromium reagent bonded to the oxygen. Chlorine is then going to come on in as our base, okay? We don't have any hydroxide here, okay? We're going to pluck off a hydrogen. Then these electrons are going to be forming our pi bond. And then the electrons here go to chromium, which technically then we should have this 4th bond, which is going to open. If you chose not to do that, that's fine. Okay, all I required were these first 3. This 4th one, if you missed it or if you didn't include it, I didn't mark off points. Okay, these first 3 arrows are what are required in order to get still points. I didn't see many people doing that. The majority of you were able to, however, figure out that this was PCC, and that the final answer would therefore be an aldehyde. Okay, again, all you had to do was draw the result of the arrows that you did in order to get the answer, which here would be the pi bond that you formed with your drawing. Okay. Okay, so that's our answer. All right. For question 10, okay, we have an alcohol substrate and we're forming 2 different types of alkyl bromides. Okay, again, this is why I told you guys to make sure we were aware to be able to recall our reagents, so that way we knew how to create alkyl halides from alcohols. Okay, I didn't need you to specifically draw me the structure of the final product. I gave that to you. Instead, I just need you to know the difference between an alkyl bromide formed with, let's just say stereochemical inversion versus one that may look like it goes via rearrangement. Okay, so what was the correct answer for this one, where my alcohol is on the wedge and now my bromine is on the dash? What does this imply about the mechanism? And then what does that tell me about the reagent I needed to use? Okay, so we see we're going from a wedge. This is becoming a dash. This implies SN2 inversion of stereochemistry. Okay, we only learned one SN2 bromine reagent, and that was PBr3. Okay, if you gave me PBr5, I would have given you points. I don't think anyone did. This is a different version of PBr3. If you gave me SOBr2, I don't think I've finished grading this page yet. I don't think I've decided if I'm going to give points for that yet. I suppose if you included it with pyridine, I might give you partial credit. Okay, we'll see. Okay, PBr3 is the reagent I expected you to know. What about this one down here? What's the other brominating reagent for alcohol? We saw it all the time in Orgo 1. What's the other way to brominate an alcohol? Okay, keep in mind PBr3, what it does is it turns my OH into a better leaving group by attacking my phosphorus. Okay, and then we are bonded to PBr2. Okay, this is going to be positive. That's one way of making this a better leaving group. Okay. And then my bromine attacks from behind, and then this leaves via SN2. The other way to make it a better leaving group, instead of it binding to a complex like phosphorus bromide, it is protonated. What bromine comes with its own proton? Exactly, Ashley, HBr, okay? HBr comes with its own proton. It's literally bromic acid, okay? Or hydrogen bromide, okay? So HBr, the first thing it does is protonate. The second thing it does is allow water to leave. And then this mechanism can undergo FN1, which is why we see rearrangement. Okay, I did not accept HBr with light, which is not a thing. I did not accept Br2, because that would have given us the correct answer. Okay, only HBr worked. Okay. And then what about having our bromine with methoxide? What should be going on here? Methoxide is a strong, small base nucleophile, correct? Okay. This means that it can, attack electrophilic sites. It can also remove protons. And this is going to be something that for primary and let's just say methyl and primary, it prefers SN2. For secondary and tertiary, it's going to prefer E2. Okay, this is one of our 4 reagents that has this preference. Okay, hydroxide, methoxide, ethoxide, and acetylide all behave this way. So here I see a secondary alkyl halide. I should be forming a pi bond. Okay, and so our answer should be the Zaitsev alkene This should be our answer. I don't think anyone gave me this. If you instead gave me the SN2 inversion, I think I gave you a point or maybe 2 points because each of these was 5 points. Okay. So if you gave me methoxide bonded there with inversion, then I assumed you were assuming this was SN2 and I might have given you like a few points. Okay. But this was the correct answer. Okay. All right, moving on to question 11. We have now provide 2 methods for the formation of the epoxide racemic mixture, which is obviously one component. Then using only one of the enantiomers that's formed, draw the products. Okay, so what are 2 methods for forming an epoxide? I was surprised that so few people knew only one, or even that so few people knew apparently none of them. Epoxides were a functional group we were supposed to learn about, and I didn't, and I had plenty of these just be empty. So what's one method? One method we even learned last semester. Yeah, MCPBA. I didn't need to draw up the structure. I didn't need you to even write out the name. I just need you to write out MCPBA or per acid. Okay, if you just wrote a per acid, or if you wrote RCO3H, okay, I gave you points for giving me at least one of those 3. Okay, what is the other method? Two-step method. Okay, this is where we go through a halohydrin. So I need to do something like Br2 or Cl2 with water as my solvent. This would form a halohydrin. Again, I didn't need you to say that it would. I just need you to give me the reagent. Okay, and then for step 2, we need to use a base. Okay, technically we need to use a strong enough base to deprotonate the entire thing. If you just gave me NaOH, that's fine. Technically not strong enough, but if you gave me NaH or NaOH, I accepted either of those. Okay, or even NaNH2. Okay, we just need, again, a base. Okay, so this is the halohydrin method. Okay, if you gave me MCPBA and RCO3H, I only gave you points for one method. Okay, because that's one method. All right, now we have attacking an epoxide in either acidic conditions or LAH conditions with a deuterium here, so I could tag where this otherwise hydrogen would have been showing up. So I think if you forgot to include the deuterium, I just took off half a point or a point or something. Okay. All right. Acidic conditions attacks on which side, left or right? Left, more sterically hindered side. So here we go. I attack on this side. We open this up. I did require that you show me stereochemistry. Okay. So what this means is that I wanted you to show me that my attacking this epoxide only, okay, I get my OH still on the wedge. Okay. And my methyl that was kind of facing away from what I was attacking is going to be pushed forward. Okay. And then the the nucleophile I just attacked with would be on the dash. Okay, so this would be my OCH3. Okay. All right. Oops. There we go. Okay. All right. What about LAH? Is LAH a base or an acid? Let me just draw out LAH. Okay, so let's keep in mind that our conjugate lithium is hanging out over here like the carbocation, or not carbocation, like the cation stabilizer that it is. Aluminum is negative, okay? Meaning that it has extra electrons to spare, okay? There is no acid in sight here. The only thing that is reactive is aluminum tetrahydride, which is negatively charged. This is therefore basic, okay? The second step, hydronium, is what we call an acid workup, which is not present in the first step, okay? When LAH is deciding which carbon to attack. So LAH in this case is gonna attack the less sterically hindered side because it's a base, okay? So we attack here, and then this opens. In this case, our answer should be, apparently pentagons are very popular, not hexagons. Okay. Just gonna draw a circle. Okay, and then we have our wedge opening up on this side. Wedge. Our methyl being a dash. Okay. And our other methyl would, or not other methyl, our hydride would also be a dash that gets added. Like that. Okay, there we go. Go back down to size, and then we have our deuterium and our OH. Okay, these have to be on opposite sides. That's how we attack epoxides. Okay, is via SN2. So we have this inversion of stereochemistry. Okay, so we have our OH here, attacking from, or not attacking, being attacked from the front, so, or from the back, so it gets pushed forward to the right side, stays on the wedge. The nucleophiles on the back side. So we see again this trans configuration. Here, the deuterium again also attacks from the back. The OH gets pushed forward. Again, the OH is on the wedge, the deuterium is on the dash. Okay, these are the stereoisomers that should have been formed. All right, question 12. Wrap this up. So question 12, all of these reagents started with the same starting material. Okay. SOCl2 with pyridine. What is this going to do? What does this attack? What does it do? For those of us who thought that SOBr2 did something, okay, SOCl2 is the SN2 of alkylating alcohol. Okay, with pyridine present, it's SN2. Okay, so what this means is that my OH here, I need to see some inversion at this stereo center. Nothing would happen to this other bromine. Okay, so we're just gonna have our just say I'll have a wedge here. Not a wedge, a dash, excuse me. Okay, oh, this is not a arrow, a line. Okay, so our bromine stays over here as a bromine. Nothing happens to that component, and then this is going to be a Cl. Okay, energy inversion by flipping the wedge to the dash. Okay, what about using concentrated HBr? Okay, this is one of the reagents we saw in the previous slide. Okay, again, we're going to protonate our alcohol, turn this into essentially a good leaving group. This will then leave. Okay, when it leaves, I will then have a carbocation. We'll have boom, 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 boom. Okay, with bromine still hanging out at the end. Oops, come back. Sorry. Okay, and this will be my positive charge. And then my bromine is going to, or the bromine that is, the bromine that is the conjugate base of the thing that protonated my water to begin with is going to be able to attack. And I'm going to end up with a racemic mixture of both of my bromines being bonded here. Okay, we'll have a bromine here. Let's just say we have a wedge. CR, and then technically I needed to have put at least shown 1 enantiomer and said plus enantiomer. Okay. What about NaH? What would NaH do in this situation? HBr is an acid. What is sodium hydride? It's a base. Exactly. Okay. So it's a base. What would a base do to this molecule? Deprotonate it. Exactly. Okay. So all I need to do is remove this proton. Okay. This is therefore going to be negative. And what would a negative oxygen do in the presence of an alkyl halide? It would attack itself. Yeah, an SN2. This is a version of the Williamson ether synthesis. Okay, it's just intramolecular. Okay, so this is going to be a 1, 2, 3, 4, 5-membered cyclic ether. Okay. All of it. There we go. We have our oxygen here. Okay. Then our wedge is just going to be hanging out over here. Okay, I didn't see anyone get this one right, but this would just be a Williamson ether synthesis, okay, where I'm doing a cyclic ether with the alkyl halide bonded on the same substrate the oxygen is part of, okay? What about this one down here? What is this? Trimethylphenol chloride. It's a protecting group, right? This is TMSCl, okay? Trimethylphenol chloride, TMSCl with pyridine. Okay, this protects alcohol. Okay. So in this case, I would protect my alcohol. to turn into TMSO. And my bromine would still be over here. Okay, what should hydroxide do now? What would hydroxide do to this structure? Hydroxide is a base nucleophile, right? It's one of those group of 4. So strong, small, base nucleophile, okay? Which means that for methyl or primary, okay, we're doing SN2, and for secondary or tertiary, we're doing E2, okay? Again, this is going to be the case for hydroxide, methoxide, ethoxide, and acetylide. Okay, so we see here a primary alkyl halide. We're therefore going to do SN2. Okay, and then the B protecting group is TBAF. Okay, so we're just going to end up with a diol. Okay, we're going to have our OH back. And then this would be an OH as well. Okay, so we ended up with an alkylating agent, 2 of them. Okay, we ended up with a Williams-Neither synthesis, intramolecular, and we ended up with a protected group. Okay, this was by far probably one of the, I wouldn't say trickiest, but probably the most complex question, because it required you to think a little bit beyond what we were just learning in class. Okay, each of these, made sure we were familiar with the mechanisms as well as how to use them effectively, and then, SN1, SN2 concepts from Orgo 1. Okay, question 13 now pertained to chapter 16, and this was, I think, pretty straightforward. You either knew how to do these or you did not. Okay, I didn't make any of these tricky. These were just, straightforward. Okay, so we see we have HCl with 50 degrees. This is warm. Room temperature is 25 degrees. So I'm basically doubling room temperature. Okay. When we use HCl, okay, the first step should be using one of our pi bonds to pick up a proton. Okay, this is a symmetric alkene. So I didn't even give you any sort of possibility. If you used either of these pi bonds, you would have gotten the same answer. Pick up a proton, chlorine leaves, okay? And then we end up with this pi bond still here. Again, you could have used either pi bond, that would have been fine. And then we have a positive, okay? Positive hangs out at the tertiary position, it's just more stable, okay? This is in resonance, correct? Where we have the, oh, let's just see, can I get it? Yeah, okay, so this is in resonance where the other resonance structure looks like this. Okay, which of these resonance structure is going to lead me to a more stable final product? The answer should be the second one. Not only because I should be thinking, okay, thermodynamic here needs to be usually that I need to wait for resonance to occur for my bromine, or excuse me, chlorine in this case, to travel a little bit farther, maybe overcoming a little bit of activation energy to get to this position, okay? Not only that, but most importantly, which one of these pi bonds is more stable? It's the tetra substituted, not the tri-substituted. This is going to be the most stable pi bond I can form. So this is where the chlorine should bind in my final product. Okay. And because I have a chiral center being formed at this position, I technically should have this plus its enantiomer. So one of these plus the enantiomer. I haven't gotten to grading this page yet, so I'm not sure if I'm going to take off points for not showing me the enantiomer or not. Technically, I do say show me stereochemistry. We'll see. Okay. All right. This would have been, again, the final product. Okay. What about the second one? What's going on here? What type of reaction is this? This one, just to be clear, was electrophilic addition to diene, thermodynamic. Okay. Does anyone know what this reaction is here? This is a retro Diels Alder. Okay, we see our six-membered ring. You can see it a couple of different ways. You can see it either here or here. Okay, we see the pi bond and we see two six-membered rings. The way that I should break this up is so that my electron withdrawing groups, which are the aldehydes here, are on my dienophile, and the R groups, which are just going to be the other part of this bridge, are going to be part of my diene. Okay, all I'm going to do is push, so the electrons move here, this moves here, and then this needs to move here. Okay, and so then I end up with a six-membered ring. Okay, not my best. Boom, 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 boom. Okay, six-membered ring that has two pi bonds because we obviously need to have a cis diene. Okay, and then I need to have a dienophile in which one aldehyde group is positioned in one way and the other aldehyde group is positioned in the other way. So we can see here, one is to the left and one is to the right. Okay, this was an example that was almost exactly like we saw on the slides. The only difference was that I think the electron withdrawing groups were cyanides. Okay. What about this third one? Okay, this is an electrocyclic ring closing. Okay, this is a 6 pi system. Okay, in order for me to do this correctly, I need to get all of my pi bonds in the ring-like conformation. Okay, so I need to do some rotation of these bonds. Okay, if we can draw a rotation arrow, that would be wonderful. Nope, okay, fine, we're just rotating. All right, hopefully this is clear. So this is gonna be like this. Nope, that, there, and there. Okay, I'm gonna have one of my pi bonds like this, one of my pi bonds like this, and one of my pi bonds like this, okay? Notice that this one is an S cis, okay, and it has this methyl group coming off of it. I still need to put that methyl group there. Same thing here. This one is S cis, okay? So I need to have this methyl group coming off here and this methyl group coming inward. Okay, I'm just going to draw it like that just for the sake of it. This is S trans, okay? So while this is here, I'm going to have the other R group pointing away. Okay, so this is one way to show how these are facing inward and this one's facing outward. Okay, this is the correct orientation I need in order to get my ring to be able to close, to have my transition state be cyclic. Okay, we can also draw this from a side view. Okay, in which again, we're going to have our methyl group here. This group will be pointing out, this group will be pointing in. Okay, and then this is the other branch right here, pointing this way. Okay, pi bonds like Okay, pi bonds like so. Let's pi bond with this one. There we go. All right. Now I just have to say, okay, I'm in a 6 pi system, okay, without having to worry about drawing the orbitals. 6 pi with heat, or excuse me, light, means that this should be CD, DC. This should be contrarotary, conrotary, meaning in opposite directions. And it should also be D, 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 D. It should also be opposite symmetric, symmetric. It should also be opposite in terms of the, what's the word? In terms of the lobes or the orbitals, opposite orbitals. Conrotary means same way is the way we're going to be rotating. I think it's technically contra-rotary. Okay. All right. So I can either rotate them both clockwise or then both counterclockwise. Okay. Or I could focus on the orbitals, which are going to be, one is going to be positive and the other is going to be negative. Okay. Here's one orbital, here's another. Let's just say, okay, this is about filling the orbital, whatever. One filled orbital, they're opposite. Okay. And so in order for these to be the same phase, okay, this one we need to rotate this way. And then this one would also need to rotate clockwise as well. Okay. This would therefore push this group down, and this group would also go down. Okay. This group rotates clockwise, so does this group. They're both going to end up down. So our final answer should be one in which I have both of my groups, let's just say on the same side. So I'm going to have, let's focus on the wedges because those are easier to draw. Yeah. Okay, we have one wedge like this. Another wedge like that. My pi bonds are going to be like so. And I do my rotation. Okay, and then of course I can't forget the other substituent. So here I have a carbon group coming off here, and here I have a carbon group coming off here. Okay, and I'm also going to have, like I said, the enantiomer in which both of these could be facing down instead of up. Okay. All right, this last one, what type of reaction is this last one? Yeah, it's a Claisen, okay, a co-rearrangement with oxygen, okay? So again, all I needed to do was point this one downward so I could have seen the cyclic reaction that was going to happen. Let's get rid of this, okay? And then the rearrangement would have worked like this, where I would have had this arrow moving here, this arrow moving here, and this arrow moving here. Okay, I could have done it the opposite direction, that would have been fine. Okay, the key here is I need to form a carbonyl, okay, and break the bond between the allylic pi bond and the oxygen. Okay, so then this would have given me a new pi bond here. Okay, and oxygen here and here. Okay, basically all I'm doing is forming an ester in this case. Okay, oh, there you go. Okay. Any questions about these reactions? Okay, last page. Okay, we see our question regarding drawing the Diels Alders product. Okay, here we have our, and we also had to identify electrophiles and nucleophiles and drawing the orbitals for these reactions. Okay, all I needed you to do was draw the HOMO and the LUMO of the diene and the dienophile. That was it for the orbitals. We also needed to identify that the diene was our nucleophile, excuse me, electrophile. No, this is the dienophile, my bad. Dienophile, this is our electrophile. And this is our diene. And this is our nucleophile. Okay. Then what we have to say is, okay, well, let's just draw the product just to get that over with. Okay, I'm going to have my diene. R group, R group. Not what I wanted. So we're just going to draw like this. Okay. Boom, 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 boom. Oxygen. Pi bond here. Not there. Pi bond here. Okay. Okay. So now we have everything aligned. Let's see how these arrows work. Okay. Again, we just do this cyclic structure here. And then this pi bond has to shift as well. There. An arrow. There you go. Okay. All right. So now what this means is I'm going to get my standard 6-membered ring. Okay, with my pi bond newly formed there. Okay, I'm going to have these guys either be wedges or dashes. Let's just make them wedges for now. Okay, these groups coming off. And they just need to be the same stereochemistry because they are on the same side. They're both out groups. Okay. And then I need my ring to align. Okay, in order for us to have the endo preference. Okay, the final product is going to be the major product. So again, I haven't figured out if I'm going to take off points for showing major equals endo. Okay, so that means my out groups are aligning with my electron drawing groups. So these should both be wedges as well. Okay, forgive me since I'm just drawing with my mouse on a computer. Do the best we can. Okay, oxygen, oxygen. Okay, so here's our major product. All right, this is the endo. The enantiomer of this is a meso compound, so we don't need to write anything about the enantiomer. Okay, but this is the appropriate compound. Okay, excuse me, with one exception in that I need to include these two carbons here to show my bridge, okay? Because there is a bridge formed with these bits. Just say I put a bond here. Okay, and there's my bridge. Okay, there we go. All right, that's my final product. When we are drawing the orbitals, okay, for the diene this is just going to be 2 orbitals, okay, and this should be the HOMO, I guess. No, excuse me, the highest occupied, the LUMO, because it's an electrophile. For our dienephile, or diene, excuse me, I need the HOMO of the 4-pi system. Okay, so this would be the HOMO. Just say this is where we're coloring it in. Okay, so let's just start here, same thing. When it comes to the HOMO, this is going to be the highest occupied. So remember with the 4-pi system, this is going to be the second one, where we have our electrons. So 1, 2, in which everything is in phase. 3, 4, in which we should have 1 node. Okay. So this is the, oh my gosh, this is the HOMO. Okay. The LUMO, again, should be the highest unoccupied of the 2-pi system. So here we have the lowest one should be occupied. Okay, the highest one should have 1 node. Okay, so here's our LUMO, here's our HOMO. This is going to be similarly asymmetric. Okay, so what I can tell so far, no one was able to give me an appropriate reason as to why this reaction only happens in heat, aka the ground state. This reaction only occurs under heat conditions because the asymmetric orbitals of the ground state overlap, but the symmetric orbitals of photochemical state would not. Okay, so if we looked at any other orbitals, we wouldn't be able to do this reaction. Here, this is asymmetric for C1, C2. Here, this is asymmetric for C1, C4. Okay, all right. When it comes to the synthesis for this last question, okay, we've got an epoxide. So this is obviously going to be our electrophile. We need to start attacking it with something. Okay, I see immediately a particular way to get a nucleophile bonded to my epoxide. And look, it's bonded to the beta position of an alcohol, AKA, looks like I am breaking open something that is going to be via an epoxide opening. Okay, I see a methyl group. Okay, and here's my methyl group. Okay, so which carbon am I attacking of my epoxide? I'm attacking the more substituted side. Okay. This should therefore be acidic condition. Okay. With the appropriate nucleophile, which we know is HO or methoxy or methanol, HOCH3. This should be it. Let's just say first thing I do is use methanol and acid. I didn't even make you guys give me a particular acid. I just needed you to indicate this was acidic condition. You could have used sulfuric acid, acetic acid, could have even used hydronium. Okay. Key here is that we'll go through this protonated intermediate. Okay, we would then have our methanol attack the more substituted side, and this would open. Okay. Boom, boom, boom. So here's my OH. Here's my OCH3. Okay, I'm going to do a deprotonation step that I'm not including. Okay, and then this will be a dash methyl that would be pushed out. Okay, how do I then get from here to here? All right, I can do this in like 2.5 steps, essentially. What's missing between this and this? Okay, the only major difference is this ethyl branch. How do I add ethyl branches directly to a carbonyl group? Excuse me, directly to the alpha carbon of an alcohol via a Grignard reagent. Okay, how can I use an alcohol to give me something that could be attacked by Grignard? Well, I need to then appropriately oxidize it into a carbonyl. Only way to do that would be PCC, so I can get to an aldehyde. Oxygen. Okay, then what do? I have to attack it with the appropriate Grignard reagent. Okay, this is literally just going to be using ethyl Grignard or ethyl magnesium bromide followed by an acid workup. Okay. See. Okay, this is really just a 3-step reaction. Okay, we attack and add an R group to an epoxide. We oxidize, so then we continue adding R groups, and then we use a Grignard reagent followed by an acid workup. Okay, and that was the end of the exam. Okay, I gave you all 2.5 hours to do this exam, if not technically, let's see. Yeah, 2.5 hours to this exam. Okay, you were able to stay until noon if you would have liked to. I just did it on the computer with my mouse in 2 hours and 40 minutes, meanwhile explaining everything. Okay, and taking time for questions. So hopefully this, goes to show that this exam could have been done if you knew how to study for everything. Okay, if you knew what to, write in. This was definitely one of those, you either knew it or you didn't. Okay, you didn't have a lot of time to necessarily just like wax poetically about what the correct answer could have been. Okay, all right. And it seems like, again, a lot of people suffered from just simply not reading the directions. Okay, all right. So I hope that this gives you guys some perspective on how to approach exams in the future. Okay, my next exam will definitely include components of these types of reactions, just for the sake of making sure we understand it. Okay, I'm not gonna maybe make half the exam chapter 12 and 13, but it will be components of the stuff that we'll need to know for the next exam. All right, on Monday, tomorrow, we are gonna just start by writing up some reagents on the board that are worth going over for the sake of retrosynthesis and understanding what's going on. Okay, we'll maybe go over some basics about SN1, SN2, and some basics about E1, E2. Then we'll talk about aromaticity. Okay, so I am going to be posting some slides about SN1, SN2 on Blackboard under Orgo 1 review. Okay, if you're still struggling with that, which I know many of you are, I encourage you to look at those slides so that way you can maybe get a better handling on what is actually going on. I'll also provide some practice questions. I'm not going to be giving the answer key for those practice questions. What you'll have to do is come talk to me and show me what your answers are, and we can discuss in recitation what your answers are, okay? And I'll be able to tell you what you need to work on, okay? But I don't want to give you the answers and risk you guys just simply looking at the answers, thinking you understand it, and then actually not understanding it at all, okay? All right, so any last minute questions before we wrap up, guys? Sorry, this went a little bit longer than expected. Is anybody still listening? No questions. All right, guys. Fantastic. So I'm gonna render this recording. It'll be up if you know, if your friends weren't able to join us, or for those of you who are at work right now, then you'll be able to watch this at a later time. I'm gonna do my best to finish grading the exams tonight, so that way I can give them back to you guys tomorrow. Okay. I will be posting the recording to Blackboard tomorrow. I just need to wait for it to render. Okay. All right, guys. Any last minute questions? Awesome. All right, everyone. Have a good night. Thanks for joining, and I'll see you tomorrow.